Since we know that radiation can be emitted and absorbed by a surface simultaneously, then we must now be able to compute for the net radiation heat transfer from a surface. This is denoted by Q over dot rad. For a real surface, the net radiation heat transfer is computed by subtracting the rate of absorbed radiation from the rate of emitted radiation. Now we can simplify this formula by setting some assumptions. First, we can say that the irradiation G is simply the emitted radiation from the surrounding surfaces of the material. In addition, we can also assume that the surrounding surfaces can be considered a blank body. Under this assumption, we can write the formula for irradiation in this way, using Stefan Boltzmann's law. This will let us write the formula for the rate of absorbed radiation in this way. Now another assumption that we can set to simplify the formula for net radiation heat transfer is that the surface of the object can be considered a gray surface. In the context of radiation heat transfer, gray surfaces are surfaces in which its absorptivity is simply equal to its emissivity. Under this assumption, we can therefore substitute the emissivity of the material for the absorptivity in the formula for the rate of absorbed radiation. Now we can simplify the net radiation heat transfer from material in this manner. It must be noted that when the result of this equation is positive, then that means that the object is gaining thermal energy. Otherwise, if it is negative, then the object is losing thermal energy. The net radiation heat transfer is obviously a function of the fourth power of the surface and surrounding temperatures. Therefore, to linearize the formula, we can use the radiation heat transfer coefficient, which is denoted by H sub r. It is computed using this formula. After computing H sub r, we can now write the formula for the net radiation heat transfer in this way. Lastly, since both convection and radiation occur at the surface of an object, we can account for the contributions of these two modes of heat transfer using a single parameter. This is accounted for by the combined heat transfer coefficient. To compute for this, we note that the total rate of heat transfer from a surface of a material is the sum of the rates of convection and net radiation heat transfers. In this formula, we can safely assume that the free stream temperature T sub infinity is just equal to the surrounding temperature or to the temperature of the surrounding surfaces T sub source. Under this assumption, we can now write temperature or we can now write the equation for the total rate of heat transfer from the surface in this way. The combined heat transfer coefficient, therefore, is simply the sum of the convection and radiation heat transfer coefficients.